Now we're going to get down to like what you need to be able to do. And so for all the weirdness in the videos that came before this one in this unit, all you have to be able to do is put arrows in boxes. What are the boxes? Well, the boxes are our Offbob diagram or our electron energy diagram. Again, remember, these all represent different shaped spaces that electrons might be around the nucleus. So there are three rules that allow us to fill this Offbob diagram. So if you're asked to do an electron configuration, look on the periodic table, find the number of electrons, and follow this set of rules to put the arrows in boxes. First rule, same name as the diagram itself, is the Offbob principle. At ground state is the lowest possible energy an atom can have. So at ground state, electrons occupy orbitals of lowest energy first. This is the Connect 4 rule. You ever play the game Connect 4? You have to have checkers on the bottom row before you can start putting them on the second row. Third row, fourth row, so on and so forth. So if we drop an electron into this diagram, metaphorically speaking, it's going to fall all the way to the bottom to the lowest unfilled orbital. Second rule is called the Pauli exclusion principle. Pauli exclusion principle says that an atomic orbital may describe at most two electrons, provided they are opposite spin. We talked a little bit about this in the last video. What is spin? Well, again, an electron literally spins on an axis, creating a north and a south magnetic pole. And so if you have this electron spinning in this direction, the next electron spinning in the other direction will allow those two electrons to be in the same place at the same time. All right, so let's look at the third rule, Hunds rule. When electrons occupy orbitals of equal energy, they fill one in each orbital with like spin before pairing. Take a look at this diagram and think to yourself, where do we have orbitals of equal energy? Anywhere that there are more than one orbitals in a sublevel, remember the sublevels are the letters, S, P, D, and F. Anywhere there are more than one orbital in a sublevel is where you have orbitals of equal energy. So for instance, 3p or 4d or 4f. And so when you are filling those, you're going to fill them all one at a time before you can go back and put a second electron in each orbital. Again, the electrons are just arranging themselves in the lowest possible energy arrangement that they can. And one of the things that generally in science translates to low energy is symmetry. And there's better symmetry for having one electron in each orbital rather than, say, two electrons in an orbital and no electrons in the other two orbitals, or two electrons in one in a second, and zero in a third. If you get that kind of half-filled orbital, that's kind of an intermediary low energy level between that and a completely filled orbital, or sublevel, I should say. Okay, so those are the three rules. So Offbob, Pauli exclusion, Hunds rule. Let's look at the Offbob principle again real quick, because you need to understand kind of some stacking involved here. So we fill lowest energy first, but as you get more sublevels in an energy level, each sublevel is a little bit higher energy. And so what happens then is a third energy sublevel might be higher energy than a fourth energy sublevel of a different type of orbital. And so we'll look at that now. So you think about this blue line there as kind of our energy that we're at. So the first two electrons will go in the 1s, and then we'll fill the 2s. And then we'll fill the 2p. So once the 2p is full, we can go and fill the 3s, and then the 3p. And here's the bit where you need to see if we increase that energy. Because those sublevels are stacked, 4s actually is going to end up filling before the 3d fills. So then we'll fill the 3d, and then we go back to the fourth energy level with the 4p, but then once again the 5s fills before the 4d, and then the 5p, and then the 6s. And if we overlay those lines instead of going at a sequence, but we put them all in there at a time, what do you see? There is your quantum ladder. And that is why as you get higher and higher energies, those energy levels get closer together, because at higher energies there's more and more sublevels, more electrons crowding around. I sometimes like to tell people to think about if you had like a room full of high school students and you put a table, say, in the middle of the gym, and you filled that with like the best possible snacks you could. Caramel popcorn, and I only said that because I'm eating caramel popcorn right now. And sour gummies, and full-size candy bars, and I don't know, slices of fresh pepperoni pizza, and you just put it all on a table in the middle of the gym, and then told everyone, like during passing period, anybody who wants free food or free candy, run to the gym. Well, what's going to happen? The first group of people that get there are going to belly up to the table. They're going to be have the ones that are going to have the easiest time getting what they want. Where are the next group of people going to come in? They're not going to form a line. They're going to go in between the shoulders of the people that are standing around the table. And then you got to think about what happens to the next row of people. Well, they're going to try to find cracks and creases and crevices and to reach their arm past someone. If they're really tall, they might try to go over somebody's head. If they're really short, they might try to squat down and get in between people. But you have this kind of situation where the more and more people that try to get at the center of that table, the more complicated the arrangement of people is going to be, the more chaotic it's going to be, and the closer, of course, everyone's going to be together. And so that's kind of what we're looking at there. So how does that go? You might think about a sodium atom and how we would go about putting electrons into the sodium atom. Well, sodium has 11 electrons if you look on the periodic table. So where's the first one got to go? It's got to go in the 1s. Is it going to go up or is it going to go down? Doesn't really matter. Again, up and down just designate two different arrangements. Where's the next one go? Well, the next one has to go down. If the first one goes up, the second one goes down. Where's the next one go? Well, it's going to go in the 2s now because the 1s is filled. Okay, that's the Offbob principle. Up or down. Here I've put down. Again, it doesn't really matter. It's just a designation. Okay, that gets us to 4 electrons. Where does the 5th electron go? It goes in the 2p, in the x, the y, or the z. Doesn't really matter. Again, x, y, and z, just differentiate them. They're all equal energy orbitals, so we might put one down. Where's the next one go? Well, now it does matter on two fronts. It's got to either go in the x and the y, and according to Hunds' rule, when electrons occupy orbitals of equal energy, they fill one at a time with like spin. Since we put that first one down, the next one has to go down. Okay, where's the next one go? Has to go down in the 2px. So that's 4, 5, 6, 7. We're trying to get ourselves to 11. Next one is going to pair up. Could pair up in the x, could pair up in the y, could pair up in the z. Doesn't matter. But then the next one's going to pair up in one of the other two. And then the last one there might drop into the z. Could have just as equally paired up z, x, y. Again, order is immaterial and there's no way for us to know for sure anyway. So there's 10. We need one more electron. We're going to drop that into the 3s. And so that is the 3s, or that is the electron or energy arrangement for sodium. Now, it's kind of a pain to draw those boxes all the time. And so what we do is we have a way to write this that's a little less cumbersome, and it's what's called an electron configuration. So we start with the first term in the electron configuration is 1s2. We don't say squared. It is a superscript, but we just say 1s2. That means 2 electrons in the 1s orbital. The next arrangement is 2s2. Then we go to the 2p. We don't worry about in an electron configuration designating x, y, and z. We just say 2p6. 6 electrons in the 2p orbital. And then the last one is 1 electron in 3s, and so that is 3s1. So that is your electron configuration for sodium. You always want to go back and check these numbers, right? So we have 6 and 1 is 7, 8, 9, 10, 11. So that accounts for the 11 electrons. Okay, so what about zirconium? So draw yourself an electron orbital diagram or an Offbob diagram. You can use lines instead of the boxes here, but you should recreate this diagram and you should plug in the arrows where you think they belong. Get yourself up to 40, and then we'll go through and look at what the electron configuration is. Alrighty, pause the video and do that. Okay, hopefully you did that. Let's go ahead and take a look at it together. We're trying to get 40 electrons for zirconium. The element symbol for zirconium is Zr. Again, you can just kind of count up the boxes: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 22, 24, 26, 28, and then there will be 2 more electrons in the 4D. And so go ahead and roll through that. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We fill up that 3D. Now wait 1 second here, because once we have a filled orbital, what we're going to do is change the order and keep all of the 3's together, even though the 4s fills before the 3D. So we want to keep all of an energy level together in electron configuration. Then we get 4p6, 5s2, and then the last one is 4d2. Now, I'm going to leave the 4d there on the end because it's not filled. I'm not going to move it back with the rest of the 4. So we always want the unfilled orbital, or the orbital is in the process of being filled, on the end of the electron diagram. And that is how you do electron configurations.